Factors that affect solubility. One of the factors that affect how soluble something is going to be temperature. And generally speaking, for most solids, the higher the temperature is, the greater the solubility will be. So generally solids increase the solubility when you have a higher temperature. So a warmer solvent means you're going to be able to dissolve, provide the energy to break apart the solid, and allow it to dissolve into solution. Liquids tend not to be affected by the temperature. Their solubility tends not to be affected by temperature. Generally, they're already having enough movement to interact with each other, so temperature tends not to affect the solubility of liquids. It does affect the solubility of gases in the opposite way as solids. So increased temperature decreases the solubility of gases. And you can think of the gases already having lots of energy, and so if you give them more energy, they're more likely to leave the solution that they're in and go back into the gas state. So actually by cooling things down, you can allow more of them to dissolve into water. And you've seen this anytime you've taken a cold glass of water and left it sitting on the counter. These little bubbles will form because as the temperature of the water rises, the particles of gas that are in the solution will come out and group up and form these bubbles. So the molecules will go from their aqueous form in the solution and group together back into a gas form. Temperature decreases the solubility of gases. Pressure, on the other hand, makes gases more soluble. And you've seen this anytime you've dealt with any sort of carbonated beverage. You can release or let go of the pressure, decrease the pressure, and the gases will come out of solution and go back to the gas state. If you increase the pressure, this is how soda streams work, is they increase the pressure and they will put gas molecules into solution. You can carbonate a beverage, and it's not until you open that up they'll come back out when the pressure is released. The size of the molecules is going to have an effect on solubility as well. Generally, small molecules are more soluble. And you've seen this anytime you've done some baking. Sugar dissolves quite well into water. Sugar is not a really small molecule, but it is much smaller than flour. They're pretty much the same thing otherwise. Flour is essentially made of sugar, but flour is really big long chains of sugar molecules. And anytime you try to mix them, it's much more difficult than trying to mix sugar and water. Don't know what happened there. This does not apply for ions though. Generally small ions tend to be less soluble, and this is different because ions form this crystal lattice structure. So small ones or ones with large charges tend not to want to leave their crystal lattice, so they will be hard to dissolve. Molecules not being ionic, smaller ones will dissolve more easily. Polarity is going to have a huge effect on solubility. So water itself, and generally when we talk about solutions and solubility and solvents, we're probably referring to water. So water is a polar molecule, and it will want to dissolve other things that have charges like it does. Those are the sort of things that it's most wanting to interact with. So ionic compounds, which definitely have charges, are something that water wants to interact with. The ion and the charge on the ion and the dipole in the water are going to be attracted to each other. So ionic substances tend to dissolve into water, they'll be carried off by water, unless the intramolecular forces are stronger than the forces between the water and the ions. So if the crystal itself has very strong forces, things like small ions or highly charged ions, they may rather stay together than go off into the water. Otherwise, water will be able to pull apart the ionic crystal and the crystal will dissolve. Polar molecules will tend to dissolve as well. So something like ammonia has dipoles to it. It is a molecule. It does not have full charges, but it will interact with water because it does have dipoles, so it will tend to dissolve fairly well in water. If it's a really big molecule though, like say a molecule, the molecules that make up flour, they are really big. They do have charges, but they're too big. They would have to disrupt a huge amount of water molecules in order to dissolve into water. So bigger molecules tend not to dissolve very well. Non-polar molecules tend not to be very soluble. Unless they're really small, they don't interact well with water because water would rather, so here's some water here, here's some oil here, they tend to stay separate because all the water molecules would rather interact with each other than interact with the non-charged oil molecules. So water tends to stay together, leaving the oil out of the water, which we would refer to as oil not dissolved. Water molecules, and here's a better diagram here, so they would really like to hydrogen bond to each other. If something wants to come into water, if something wants to dissolve into water, you've got to disrupt those hydrogen bonds, and that takes a bit of work. If it's a really big molecule, it would have a lot of disruption to do, and that's not going to happen. So the oil would stay separated, and the water would stay separated. Not that they're not attracted to each other. Any particles are going to have some sort of attraction to them, but it would take too much disruption of water to get those large oil molecules in. Non-polar solvents. So let's say we're not dealing with water. Let's say we're dealing with something like bromine. So if we have bromine as a liquid, or say we have iodine as a liquid, so we have a non-polar solvent, depending on the temperature we'd have. They are not polar, so they are not particularly attracted. They somewhat attracted to each other, but not hugely attracted. So two bromine molecules will have some very weak London dispersion forces only keeping them together. So if you wanted to put some iodine into some bromine, that would be relatively easy to do because you do not have that hydrogen bonding that needs to be disrupted. So non-polar solute dissolves non-polar solvent quite easily. They're happy to mix together because neither one is polar. They have no problem interacting. So in summary, we say like dissolves like. This tends to be true. And of course, there's always exceptions. The size of the particle is going to matter. The type of ionic charges and size of the ions is going to matter. But generally speaking, things that are like tend to dissolve things that are like. Polar solvents, which have a charge on them, dissolve charged solutes, things like ions and things like other molecules that have dipoles. Non-polar solvents tend to be quite good at dissolving other non-polar solutes. They have no problem interacting, neither one is charged, so they do not exclude each other from the mix. Solubility curves are a way of showing how much something dissolves. So they tend to have the amount of solute that will fit into 100 grams of water. They have that on the left here. So the solubility in grams per 100 grams of water. So this right here would represent 50 grams of solute dissolving into 100 grams of water. Water being water, 100 grams is equal to 100 milliliters. So this is essentially the solubility of different things represented dissolving into 100 grams of water per unit of degrees Celsius, per temperature. Generally, as we said earlier, as temperature increases, the solubility of solids will also increase. So here's 3 different solids, and as you can see, as temperature rises, their solubility does increase. It's not the same for each solute though, so we can show this as a curve. Then we can see if we can apply this. So, for example, what kind of solution would have 125 grams of sodium nitrate dissolved at 80 degrees? So you look at your graph here and you say, okay, well here's 80, and I want to look at sodium nitrate. So if I look at sodium nitrate at 80 degrees, we're talking about right here. We're right on the solubility line for sodium nitrate. So that would hold right between 100 and 150. That would be 125 grams. So if you have a solution that has 125 grams of sodium nitrate and it's at 80 degrees, it's right on this line. And so that line there, that is what we would call a saturated solution. So if you're on the line, you're talking about a saturated solution, which means if you have more solute at a given temperature than what it would be on the line, you would have a supersaturated solution. If you have less solute, so lower down on your x-axis here, you'd have an unsaturated solution. So the line represents the saturation point of that substance at different temperatures. So what kind of solution would we have if we had 50 grams of sodium chloride dissolved at 70 degrees? So let's say, okay, 70 is somewhere right here. So if we go up to our sodium chloride line right here. So if we had 50 grams, that would be right here. So normally sodium chloride would be saturated at 70 degrees. It would be saturated with less than 50 grams, or whatever that worked out to be. So if we happen to have more, if we had to have it at 50 grams, we're definitely above the line at 70 degrees. So we have more solute in the solution than what the solution can hold at that given temperature. So we must have a supersaturated solution. If we wanted to put 50 grams of sodium chloride in, we'd have to increase the temperature all the way up here to 90 degrees. Then you would be able to have that amount in. That would be a saturated solution. At 53 degrees, a saturated solution of sodium nitrate, how much does it have in there? So let's say there's our 50 degrees. Let's follow up to our sodium nitrate. So I don't know, maybe somewhere right in there is 50 degrees. So if we look at, I'm looking at the wrong one here. Right here, because the blue line is the potassium nitrate, that's what I want to be looking at. So at 50 degrees, potassium nitrate would have that much solute dissolved in the solvent. So right there, that's 75. So I would say somewhere below 75, above 50. I wrote 75 here. I disagree with that at 53 degrees. Yeah, I would say that's probably, I don't know, closer to 70 maybe. 60 or so. Obviously having a more graduated scale would give us a better answer. But that's essentially how solubility curves work. They show the curve of saturation for given solutes at different temperatures within a solvent per certain volume of that solvent, and it generally tends to be per 100 milliliters of water.